Thus far in this chapter we've talked about energy. Energy, remember, is measured in joules or in kilojoules. And most of the time in chemistry we're concerned with the type of energy called heat energy. Heat energy is symbolized by the letter Q and by a special letter H as long as it's at constant pressure. We've learned so far 3 ways that we can measure the enthalpy or approximate the enthalpy by measuring Q, or the change in heat. The first one was by using a thermochemical equation. In an equation like this, where A plus 2B goes to 3C yields 4D, the enthalpy change, or delta H, is equal to positive 150 kilojoules. What this means is for every 4 moles of D that are produced, positive 150 kilojoules or 150 kilojoules are absorbed, or for every 3 moles of C that are reacted, 150 kilojoules are absorbed. The thermochemical equation is super duper important, and you need to know how to relate the coefficients to the enthalpies of the reactants and products. The second way was something called constant pressure calorimetry. And constant pressure calorimetry usually took place in something like a coffee cup calorimeter, where the enthalpy was equal to Q because we did not have a change in pressure. And the equation for this was mass times specific heat capacity times change in temperature, where M stands for mass, C stood for specific heat capacity, and triangle T stood for change in temperature. This equation is given to us on the yellow periodic table underneath the thermodynamic data area, where it says Q is equal to MC delta T. Notice they use Q here, and they assume that you know that Q is equal to delta H because it's taking place at constant pressure. Our book does not always use a small c. Sometimes it uses a small s to mean specific heat capacity, which is measured in joules per gram degree Celsius. The other textbooks and the periodic table uses the small letter c, meaning specific heat capacity, C for capacity. And it's the amount of energy per gram degrees Celsius. For water, the specific heat capacity, remember, is 4.184 joules per gram degrees Celsius. If you don't remember that number, that's one that should probably just pop into your mind. This is also known as 1 calorie. 1 calorie per gram degree Celsius is the same as 4.184 joules. Well, the third way that we learned to measure Q or delta H was through bomb calorimetry. And remember, bomb calorimetry took place in a container that had a constant volume. And this had a similar equation to find Q, except we said bomb calorimetry isn't always exactly the same as delta H, but it's close enough that we can approximate it. And we can say Q is very approximately equal to change in enthalpy, and it's equal to the heat capacity of our calorimeter, negative C cal, because remember the substance is burned and it transfers the heat to water, times the change in temperature. Heat capacity is usually given in an amount of kilojoules per degree Celsius, and of course the temperature change is the temperature final minus the temperature initial. And this will give us our energy or enthalpy change in kilojoules. And from there you can take it and take how many kilojoules are burned, or how much of it is burned, and divide it by that amount to get an amount per gram or an amount per mole. A fourth way that we're going to learn during this video cast is using something called Hess's law to determine the enthalpy or the change in enthalpy for a reaction. And since lots of these reactions in chemistry have already been measured and tabulated in terms of enthalpy that's released per mole, it's not really necessary to do calorimetry for every single reaction. You can use reactions that have already been done to help tabulate the enthalpies for new reactions. Hess's law states that if a reaction is carried out in a series of steps or reactions, the enthalpy change for the overall reaction or change will equal the sum of the enthalpy changes of the individual steps. Hess's law is outlined for us in textual forms on page 189 in your textbook if you'd like to follow along. Pause now, though, and make sure that you have out the practice exercises. Practice exercise 5.8 is where we're going to begin in your packet, so you can take notes and write down some of the sample problems as we go along. Make sure that you have practice exercise 5.8. Pause the video now if you need to get it out. The first sample problem says that carbon occurs in two forms, graphite and diamond. The enthalpy of the combustion of graphite is 393.5, and that of diamond is 395.4. And it gives the reaction for the combustion of graphite to carbon dioxide and the combustion of diamond to form carbon dioxide. And notice the enthalpy changes are just a little bit different. And it says, calculate the enthalpy change for the conversion of graphite to diamond. And so it wants to know what is the enthalpy change for this reaction. But it doesn't give us this reaction up here. It gives us two other reactions. Well, what could I do to combine or change or add or subtract these two reactions to get this one? And that's the whole trick of Hess's law. Well, I want to have carbon diamond as a product. So I'm going to take this second reaction right here and I'm going to flip it around. I'm going to change it around and I'm going to write it this way. CO2 goes to carbon in the form of diamond plus O2. And when I do that, what is going to happen to my enthalpy change? Remember, when I take a reaction and I write the reverse of the reaction, the enthalpy change numerically does not change, but its sign changes. Because I'm doing the reaction backwards, it now does not release 395.4 kilojoules. It needs to gain 395, 0.4 kilojoules. 395.4. It's this number right here. 395. If I can write that a little bit better. Now, the reason that helps is because I can now take this first reaction of carbon as graphite plus O2 goes to carbon dioxide, and I can take this first reaction and this second reaction and add them together. And when I add those together, everything that's on the left side of the reaction comes together at once. I'm outlining it in green. And everything on the right side of the reaction comes together at once. The diamond, the carbon dioxide, and the oxygen that I'm outlining in red. And notice there are some things that are exactly the same on both sides of the reaction. Notice the O2 is present here and here. The carbon dioxide is present here and here. And so those items cancel out. And what remains is carbon graphite, arrow, carbon diamond. Exactly the reaction that I'm looking for up here. And that's what Hess's law says, is that if you combine two reactions, the enthalpy for the new reaction is simply the sum of the enthalpies of the two first reactions. And so I will take this graphite right here, negative 393.5 kilojoules, and add it together with the 395.4. Notice positive now, because remember I changed this reaction around. I switched it around. Add those two together and I'll get the overall enthalpy for the new reaction. And if I add those two together, I think I get about, about 1, something like that. I believe it's about 1.1 or so, 1.9 kilojoules, I believe. When I add those two together, this one's just a little bit more positive, which makes sense because I need to put energy into the system to change graphite carbon to diamond carbon. It doesn't take a whole lot of energy though, but it certainly does take some energy, which leads to an interesting observation. Can you convert graphite to diamond? I mean, diamonds are worth a lot of money. If I could just take simple pencil lead, which is graphite, and convert it to diamond really easily with only using 1.9 kilojoules of energy, wouldn't that be like a really good thing to do because I could make lots of money by selling lots of diamonds? As a matter of fact, that would be a great observation on your part, saying that it doesn't take a lot of energy to do. But what this does not tell us, it tells us the amount of energy needed, but what this does not tell us is about the speed of the reaction. It tells us you need to put in 1.9 kilojoules to make it happen. But when you make it happen, it doesn't tell us how fast the reaction is going to take place. And that turns out to take a little bit of time. Let's take a look at a second exercise using Hess's law. And it says, calculate the enthalpy for the reaction where it has NO plus NO3 goes to NO2 plus O2, and O3 going to 3 halves O2, and O2 going to 2 O2. And it wants to know the overall enthalpy for this reaction here on top. And so somehow what I need to do is rearrange or change these equations or these reactions so they can be added together to look like this goal reaction right here. And a lot of people like these problems because you can do anything you want to these reactions. I can multiply them by 2, divide them by a half, I can add the reactions together, I can subtract them together. Some people don't like these problems because of that fact as well. But what I usually like to do is I like to start and say, okay, my goal is to get NO2 by itself on the right-hand side. Which reaction right here has NO2 as a product? The first reaction. Well, it has NO2 as a product, so let's leave it alone. Let's not do anything with it. It has the correct coefficient, just a 1 in front of it. It just has a 1 in front of it right here. But the problem is I have a whole bunch of O2 on the right-hand side, and I have no O2 at all in this reaction. So somehow I've got to get O2 on the left-hand side so it'll cancel out. And lo and behold, look at this third reaction right here has got O2 on this side, and so the O2s are going to cancel with the O2s. The problem is that I also need in this goal reaction right here some regular O right here on the left-hand side. And if I look at it, there's no O on this left-hand side at all. So what could I do? Well, looking at this reaction right here, I could flip it around. And I could get the O's on the left-hand side, but now I'm goofing it up again because I'm putting more O2 on the right-hand side. Let's give it a try, though, and let's see what happens. I'll write 2 O's go to O2, and then when I do that, my enthalpy has to change to negative 495. Remember, when you flip a reaction around, you have to change the sign of the enthalpy. So cross this one off because I'm no longer using that one right now. And then take a look at this O3 that's in here. I don't have O3 in my goal reaction, so I'm going to flip this one around as well. And when I do that, I've got 3 halves O2 goes to O3, and when I flip that around, remember my enthalpy is going to become positive 142.3. See how it had a negative sign there? I've got to flip it around to become a positive. Now if I look at my 3 reactions, the one up here at the top, this one, and think about adding them together, what would happen? The O3 would cancel with the O3. I've got 3 halves O2 right here, and it looks like I've got 2 O2s right here. Something kind of strange right there. It looks like it's not quite working. And I have 2 O's right here, but I really only need 1 O right here. Well, let's go with what I have, and there's no particular right order in which to do this, which frustrates a lot of people. But I'm just going to take a guess, and I'm going to say, okay, I only need 1 O right here, so I'm going to multiply this reaction by 1/2. I'm going to multiply this reaction by 1/2 on both sides. When I do that, notice this becomes 1. And if I multiply this reaction by 1/2, guess what I have to do to the enthalpy? I have to multiply it by 1/2. And notice, interestingly enough, now what happens to the amount of oxygens? I have 1/2 plus 1, which gives me 3 halves O2 on this side, the total right side of the reaction if I add these together, and I have 3 halves O2 over here on the left. Oh boy, they're going to cancel out. Don't get too excited. It's going to be okay. Let's add these 3 reactions together and see what we're going to get. I'm going to take everything on the left-hand side of the reaction now. I'm going to circle it all in green so we know what it is. everything on the left-hand side of the reactions, and I'm going to put it together. And then I'm going to take everything on the right-hand side of the reactions, and I'm going to circle that in red so you know which things those are. And I'm going to put those all together, and then I'm going to see what cancels out. So I'm going to rewrite everything on the left-hand side. NO plus O3 plus O plus 3/2 O2 goes to, okay, that's everything on the left-hand side of the reaction. Now on the right-hand side, NO2 plus O2 plus 1/2 O2. Oh, hey, that together makes 3/2 O2, doesn't it? Plus O3. Okay, and if I zoom out just a little bit, I think you can see the entire reaction. And now notice what things cancel out on each side. I've got an O3 that'll cancel. I've got 3/2 O2, 3/2 O2, and I have NO plus O goes to NO2. Hey, NO plus O goes to NO2 was exactly the goal reaction you needed to do. Now, to make this happen, notice I had to flip this reaction around and multiply it by 1/2. This one I had to flip around, and then I had to take all reactions and add all three together. So when I end up doing this, I'll take this enthalpy, adding it with 1/2 of the reverse of this, and this enthalpy right here. And so when I add negative 198.9 plus negative 495 times 1/2 plus 142.3, I'll end up with an overall enthalpy change now for this new reaction, the one that I wanted to know, of negative 304.1 kilojoules. So that's another example of Hess's law, and this was a tricky one because there were a number of things going on. Not only did I have to flip a reaction around, but I had to multiply it by 1/2. Here I had to flip another reaction, then I had to take all three reactions and multiply them together. Let's take a look at one other example. Let's take a look at this carbon one right here. Here you can see there's carbon solid plus oxygen goes to CO2. Carbon monoxide plus 1/2 O2 goes to CO2. And it says find this reaction right here. Take a moment, pause the video now, and see if you can do this reaction. Given these two reactions, find the enthalpy for this reaction. So taking a look at the reaction I want to find, notice I need carbon solid on the left-hand side. That's given to me in the first reaction, so I'm going to leave that alone. I need 1/2 O2 in there somewhere. Looks like that's in here somewhere. There's O2 in both of those. Notice this is a full O2, this is a half. And then I need carbon monoxide, or CO, on the right-hand side. Notice here's CO, but it happens to be in the wrong position. It's on the left-hand side of the reaction. So let's flip this second reaction, and let's write it as CO2 goes to CO plus 1/2 O2, and now the enthalpy becomes 283 positive kilojoules. And then let's take this first reaction right up here, which was C plus O2 goes to CO2, and leave the enthalpy change the same. That equals negative 393.5. And if I add these two reactions together now, notice what's going to cancel out. The carbon dioxides are going to go away, and I'm left with C plus O2 goes to CO plus 1/2 O2. Oh! Look, 1/2 O2 will go away, which leaves me with only 1/2 O2 on this side, which is my goal reaction right here. And so all I'm going to need to do is take these two enthalpies then, add them together, and my overall new enthalpy will turn out to be negative 110.5 kilojoules. And those, folks, are 3 examples of using Hess's law. You can go ahead and give this one a try if you'd like to as well, and this one is actually worked out as sample exercise 5.9 on page 190 of your textbook if you'd like to see that example problem done for you or see the answer to it after you give it a try. Good luck with your Hess's law problems.